Hello students, in today's lecture I will discuss about parallel projection. So as I have discussed in the last lecture, projection is basically it is the display of three-dimensional object on a two-dimensional view plane. And projections can be of two types, parallel projection and perspective projection. So in this lecture I will discuss about parallel projection. So as I have already said, when the projection lines are parallel and when the projection lines are parallel and when they are intersecting to the view plane, this type of projection is called as parallel projection. And parallel projections are of two types. First is orthographic parallel projection and second is oblique parallel projection. We can specify a parallel projection with a projection vector that defines the direction of projection lines. When the projection is perpendicular to the view plane, we have an orthographic parallel projection, otherwise we have an oblique parallel projection. So here in the figure we can see that if the projection lines are intersecting to the view plane perpendicularly, then it is called as orthographic projections, and if the projection lines are not perpendicular to the view plane, then it is basically it's a oblique parallel projection. Now, orthographic projections are most often used to produce front, side and top views of an object. So by making use of orthographic parallel projections, we could able to produce the pictures and we could able to see the front, side and top views of an object. Front, side and rear orthographic projections of an object are called as elevations, and a top orthographic projection is called as plane view. Okay. Now such type of projection is basically used in engineering and architectural drawings. Commonly employ these orthographic parallel projections because lengths and angles are accurately depicted and can be measured from the drawings. So basically parallel projection is normally it's used in engineering and architectural drawings because by using parallel projections we would able to calculate exactly what the figure dimensions are, so that we could have a good idea about the picture or the image that we have drawn on the paper. Now here we could see the transformation equations for orthographic parallel projection. Here in the figure you can see that we are having a point P, which is represented through the coordinate system as Px, y, z. In projection we are dealing with three-dimensional objects, so we are having here all the three coordinate axes, x-axis, y-axis and z-axis. Now this is a dashed line, which is normally a projection line, and after that it is falling on the view plane, and we could able to get the picture of the image. So the coordinates x, y, z has been transformed to x, y. If the view plane is placed at the position z along the z-axis, then any point x, y, z in the viewing coordinate is transformed to the projection coordinates as xp is equals to x and yp is equals to y. So here you can see that xp is the projected value of along the x-axis and yp is the projected value along the y-axis. So here you can see that the value of xp is x and the value of yp is y, and we here there is a loss of one coordinate axis, that is a z-axis, but we preserve z-axis where the original z coordinate value is preserved for depth information needed in depth queuing and visible surface determination procedures. So this value of z is normally it is preserved and it could be used when we will study the concept of visible surface detection or hidden surface removal. So here on the projection plane there could not be z value because it is a two-dimensional plane, but the value of z will be preserved for further processing. Now an oblique projection is obtained by projecting lines along parallel lines that are not perpendicular to the view plane. So what is happening in this case? The projection lines are parallel but they are not perpendicular to the view plane. Such type of projection is basically called as oblique parallel projection. Now point x, y, z is projected to position xp, yp on the view plane. Orthographic projection coordinates on the plane are x comma y. The oblique projection line from x comma y comma z to xp yp makes an angle alpha with the line of projection plane that joins xp yp and x. So here in the figure you can see that we are having one view plane, and view plane is along x-axis and y-axis, but it is kept on z-axis. So here is an object having the coordinates x comma y comma z, and it is creating two types of projection. First is orthographic projection and second is oblique projection. When it is producing orthographic projection, then certainly the value of x y z becomes xy, and this projection line will make an angle of 90° with the view plane. But here we are discussing about oblique parallel projections. So what is happening here? We are having a line which is connecting orthographic projection and oblique projection, and capital L is the length of the line. And what is happening, the oblique parallel projection line is making an angle of alpha with the line which is joining the orthographic parallel projections and oblique parallel projection. Now this line of length L is at an angle phi with the horizontal direction in the projection plane. So normally you can see that this line is lying on the xy plane, and the length of this line is capital L, and you can see that this line is making an angle of phi with the x-axis. So we can write the equations as, we can express the projection coordinates in terms of x, y, L and phi as xr is equals to x plus L cos phi and yr is equals to y plus L sin phi. So from the concept of mathematics, we could able to easily conclude that the value of xr is equals to x plus L cos phi and yr is equals to y plus L sin phi. Now length capital L, we know that this line is of having length L. Now length capital L depends on the angle alpha and the z coordinate of the point to be projected. So here from this small triangle we could able to conclude that tan alpha is equals to capital Z upon L, and we can say that Z is equals to Z upon tan alpha, and 1 alpha we could write it as L1. So here we could able to say that L is equals to Z L1, where L1 is the inverse of tan alpha, which is also the value of L, where Z is equals to 1. We can then write the oblique parallel projection equations as xr is equals to x plus z L1 cos phi and yp is equals to y plus z L1 sin phi. So what is happening, we are substituting the value of L in these equations, and from this we could able to conclude that xr is equals to x plus z L1 cos phi and yp is equals to y plus z L1 sin phi. From this we could able to conclude the transformation equation of oblique parallel projection as 10 L1 phi 0, 01 L1 sin phi 0, 0000, 0001. So this is the transformation equation for orthographic parallel projection. Now from this equation we can see that if the value of L is equals to 0, if the length of the line is equals to 0, then certainly the projection will be, it could be orthographic parallel projection. So we are substituting the value of L as 0, so we could able to find the matrix for orthographic parallel projection. So the matrix of orthographic parallel projection is given as 1 0 0 0 0 1 0 0 0 0 0 0 and 0 0 0 1. So this is the matrix transformation matrix for orthographic parallel projection. Thank you.